All right, welcome everybody. My name is Douglas Bruce. I'm one of the instructors at the Laney College Biomanufacturing Program. Today we are having one of our series of lecture series guest speakers. We're welcoming Lee Asplund from Hamilton. Lee is a regional sales engineer in process analytics, and since I met Lee, we've had a number of well, at least one opportunity for a guest speaker event we did. A talk on it was DO sensing, dissolved oxygen sensing, which was really amazing to learn about. And today we're going to learn about pH in bioprocess analytics. So welcome, Lee, and I'll let you take it from here.
Thank you so much, Doug. I am really looking forward to giving this presentation to you. A couple housekeeping rules up front. Everybody is muted. I strongly encourage you to use the chat window if I ask you for some feedback, and to use the question and answer window if you have questions, and you can, I believe, up if somebody asks a question that you think is really important. I will answer questions periodically throughout if they're relevant to the current content, and I will answer a bunch of questions towards the end. If you have any problems, feel free to send a chat and Doug will see if he can help you out with that. The more you ask questions, the more you're going to get out of this. And this is being recorded. And I believe that Doug is going to be putting this up on YouTube a little bit later on. So I think we're ready to go from here. All right. So my name is Lee Asplund. I am the regional sales engineer for the Hamilton Company. We sell process analytics sensors, at least in my division. We have a few other hats that we wear in other divisions. I cover Western Canada and all of Northern California. So you'll have my contact information in a little bit. And if you have any questions, you are welcome to drop me an email. I welcome you to connect with me on LinkedIn and anything like that. And again, if you have questions, comments, use the chat, use the question answer. My whole point of being here is to answer questions for you. We're going to be talking about pH and understanding what pH is all about when it comes to bioprocess. We're going to go a little bit of an overview over pH as a whole. And then we are going to talk about the anatomy of a probe, how to choose a correct sensor in your process, calibration, some care and maintenance, troubleshooting, and then if we have a little extra time at the end and instead of doing questions, we may talk about some intelligent pH sensors. Just depends on how many questions you guys have throughout. So can anybody in the chat window tell me what pH is? Most people think of pH as a measurement of the hydrogen ion concentration, and that's what we're taught in school, but it's actually not the case. Instead, pH is actually a measure of the activity of the hydrogen ions in solution, okay? It's correlated through measurement at a specific voltage to the pH, but there's no actual way of measuring the concentration of hydrogen ions. Okay, so it's a measure of the activity. What does that mean? Well, we know, and we've seen a ton of tables on this, that hydrogen ions and hydroxide ions are dissociated from water. Okay. And we know that at a neutral solution, pH 7, those concentrations should be equal. And we know that this is a logarithmic scale. From pH 0 to pH 14, it's not linear, it's logarithmic. We know that if we increase the hydrogen ion concentration, so it's higher than that of hydroxide, that our solution is what we call acidic, and the pH drops. We also know that if we go in the other direction, and the hydroxide outweighs the hydrogen ions, that our solution is what we call basic, and our pH value increases. Okay? So what else do we actually need to know about this? Well, we need to have an aqueous solution in order to measure pH. Cannot be done in organic chemistry, not this way. So that means you need at least 5% of water in your solution. The closer to no water that you get, the more wonky your results might be. pH is also compensated, or it's very much affected by the temperature. Therefore, you must compensate for any temperature changes when you're doing your measurements. If your measurements are going all over the place because your temperature is going all over the place, you get very noisy measurements. It's also affected by the dissociation of ions. If that makes sense. If you increase the temperature, you increase your dissociation, you increase your activity. And it's logarithmic. Let's look at a few common examples, okay? If we think about battery acid, that's incredibly acidic, water is neutral, and drain cleaner or bleach are pretty much basic. Well, that's great in the world outside of biopharma and biotech, but how does that matter when we're in biopharma? Let's think about optimal cell culturing or fermentation conditions. Now, the information I give you here are some ranges. If you have a special cupcake that you have modified genetically of some cell line, it might have different pH requirements. But mammalian tends to be pretty happy right around neutral, 7.4, slightly basic. Transformed cell lines are a little bit broader. Fibroblasts, a little more basic. Insect cells like it a little more acidic. Yeast is a pretty tolerant little critter. It really prefers acidic conditions, but it can tolerate a wide range from about pH 4 to pH 8. And bacterial cell lines are about 6.5 to 7.5. Some of the things that can affect the pH in your culture during culture conditions are the temperature of your culture, the cell growth, lactic acid, and the dissolved CO2. Okay. CO2 itself, the expulsion of it during cell process goes through this basic chemical reaction. This is how dissolved CO2 affects pH. You have carbon dioxide with water, gives you carbonic acid. Just for your own reference, 1 millimolar concentration of carbonic acid is about a pH of 4.6. Okay. And in culture, you've got a bioreactor here, and you've got everything floating around. As your increased CO2, dissolved CO2 happens, you tend to see a decrease in cell growth and protein production. Okay. The ideal operating range for CO2 for a typical cell culture is between 5 and 10%. Any dissolved CO2 above 20% can actually cause detrimental effects to cell growth and to protein production. So the next thing we need to think about is the impact of pH on cell culture. And this is just a graph giving you an example. And if we look at one cell culture, example here, a difference of 0.3 pH can actually change the concentration of viable cells on a fairly significant level. All right. So if we look here, we've got one culture at pH 7.3 and one at pH 7. You can actually see your N titers between those different. A 50% increase in productivity happened at a pH of 7 versus a pH of 7.3, which is pretty significant. So it's one of those things we call a critical process parameter and something that we always need to control on. Now, again, take with a grain of salt everything I just said as far as typical, because we know in cell culture there's actually no such thing as typical. If there was, there would be no point in anybody going to school, and there would only be one critter out there that we culture. And the world would be very boring, and we wouldn't have a mad dash to see who can come up with the next most amazing vaccine, since a lot of vaccines are based on biologics. There are a lot of different approaches when you measure pH in bioprocess. The first is called offline monitoring. It's where you remove a sample from your process, and you take it over to your lab bench, and you take a measurement. This needs to be done with something called a sterile sampling technique. And I know that you guys have had some bioreactor people come in, so they've probably talked to you about sterile sampling ports on your bioreactor. Online monitoring is where samples are diverted from the flow to offline analyzers. They're sterile, but they automatically grab aliquots at periodic times during your process and feed that through this sort of robotic loop to give you sampling automatically. Those are cool when you can do it. You have to have a fairly hefty size lab for that with some robotics because they're not inexpensive, but they can give you some great measurements. But again, they are samples in time. They're snapshots. The best way of doing pH measurements is in situ, or what we call inline. And those are where you put pH sensors inside of your bioreactor for a real-time measurement continuously. The problem with both offline and online monitoring, where you take a sample and you measure it, is that's sort of like taking snapshots in time. And you might miss an entire important event that happens between those snapshots. Whereas continuous real-time processing with pH measurements in solution gives you a real story all the time, and you still might take your offline measurements to verify or validate your system. So in biopharma, pH is measured at all stages. It's probably the most common measurement technique done. It's used extensively in all stages of the biopharma process, from upstream to downstream. It's also used throughout R&D and in external processes such as water purification, wastewater treatment. If you're doing things like media development or media production at your facility, it's going to be used there as well. So it's kind of one of the most important things that you could possibly look at during your process. Next, we're going to talk briefly about the anatomy of a pH probe. Okay. I really believe it's important to understand how your probes are put together so that you understand what you're doing. So the first thing we're going to sort of do is zip over and take a look at how some different pH measurements are made. Many of us are used to litmus paper strips. This happens to be for my hot tub. But you're used to a piece of paper that's a pH sensitive dye. Those are good. They're fast and dirty, which is great if you're doing a hot tub or swimming pool. Not so good if you want actual high quality measurements. In other industries, there are metal or plastic electrodes. There's also something called an ISFET, which is an ion selective field effect transistor. These are great, except that they have a great advantage of having no glass in them, so they should be ideal for the food industry. The problem with ISFET sensors is they cannot withstand hot alkaline CIP cleaning procedures. They also cannot be autoclaved or steamed in place, which is generally what you need for cleaning. There's optical pH sensors. Those are not ready for real time. They experience tremendous drift. There have been some recent cases where those have been used with some amount of success in single use, very small, mini bioreactors where people are just doing rough crude testing to sort of do basically 20, 30 different strands at a time, and they just need to get a rough idea of where they're at, plus or minus a half a pH unit, totally fine if there's some drift. The most common sensors, however, are what we call glass sensors. And these are what is used in bioprocess. I have a range of them here. You can actually see I've got one sitting in solution, but there's other sensors that you're going to see around. If you ever go to a lab in real world and they give you a sensor like this in your lab, walk away. Just walk away. These were meant for hot tubs, maybe for waste streams, rivers. They're great for that. But they are absolutely not meant for biological. They don't have good accuracy. They cannot be sterilized or cleaned. They're just not meant for that. Then you get laboratory sensors. This is actually a higher end hot tub and water sensor. I use it in some of my hydroponics. It is closer to a laboratory sensor. This one has a plastic body, but you have really good laboratory sensors in your facility. Then we have the glass ones that have different connectors. And then you can even have glass ones that have solid polymeric. And we're going to go through all of these. But these are some of the sensors that are available within pH measurements. All right. So how does a basic pH measurement happen? Well, it's basically two electrodes that form an electrical circuit. The first is what's called the pH glass electrode. It's also known as the membrane or the measuring electrode. That is connected electronically to the reference electrode. And how do you complete the circuit? Well, there's a little liquid glass junction or liquid junction down here in the measuring solution, and a trickle of ions comes out of your reference electrolyte, trickles across, contacts with the pH glass of the glass membrane, and you get a nice electrical circuit. This reads out in millivolts. The measuring side, the business end, it has its own electrolyte and it has a silver chloride wire. The reference electrolyte or reference side also has its own electrolyte and has a silver chloride wire, as well as the liquid junction. And what you're measuring is the voltage potential of the solution. We're used to seeing this as a combined pH sensor. So you don't use two, you use a single one. And I've color-coded this so you can see pretty easily where the reference is versus the measuring electrode. Okay, you still see the reference, you see the reference electrolyte, you see the liquid junction. When they're combined, you can see the liquid junction is quite close to the pH-sensitive glass. On the measuring side, you have the buffer, the silver chloride wire, and the very special pH-sensitive glass. And in most combined pH sensors, you'll have a built-in temperature probe in the middle. And that means you're getting a pH temperature measurement at the exact same spot. You're getting your pH measurement. This is incredibly useful when you're doing temperature compensation. You'll hear a lot of people wax poetic about pH glass and how special it is. And that's absolutely accurate. It's a very special type of glass, and every manufacturer of pH probes has their own special formula. And they're never going to share it with you or with each other. But all of them work basically the same. Now, when you're looking at a pH glass electrode, the special part of the probe, the special pH glass, is only at the very end. In Hamilton probes, they happen to be blue. So this part is regular glass, and then you have the bulb, the round part at the end, and that's where your pH sensitive special glass is. So what does that glass actually look like? Well, that glass, when it forms in a liquid aqueous solution, will form an inner and an outer gel layer. And pH is measured by the difference between what that inner layer looks like and the outer layer. Keep in mind that that inner layer is enclosed, and it's in a special environment that never sees anything but itself. So it's your standard side. It should stay consistent throughout. Your glass goes here, then you have the outer gel layer. That's exposed to your process, to your solution, to your samples. That outer gel layer is permeable to hydrogen ions, but doesn't allow other ions in. And when you get those ions embedded in there, you end up with an electric potential between the inner and the outer. So it's a difference in electric potential between the inner gel layer and the outer. Okay. How does that actually layer work? Well, basically, that pH glass is embedded with lithium ions. The internal KCl solution, which is buffered, has a set number, standard number of hydrogen ions, and the process side has different, whether it's acidic or basic. Okay, so the lithium ions act as current carriers. Positive charges develop a positive millivolt signal, and that's acidic. And then if you happen to have a negative millivolt potential, that's an alkaline solution. Pretty easy to say, might take you a little bit to wrap your head around, but this is how all pH probes basically work. So the glass, the very special glass. First, I'm going to let you know a fun little trick. Hamilton has an overactive marketing department. So you'll notice that the blue bulb on the Hamilton probes, if you happen to notice that Hamilton's logo is blue, and blue is their primary color, the marketing department made the engineering department come up with a lot of hard work to try and match the blue, so that all of the Hamilton probes have blue tips because it's Hamilton blue. But what's really convenient is it actually tells you where the special glass is on a Hamilton probe. And that glass is a little different from the rest of the glass. Every manufacturer, again, has different kinds of glass. Within Hamilton, we have something called a universal glass or an H glass. There's a Phi glass, which is really awesome for steam in place or autoclavation. So it's used a lot in any bioprocess. And we have an HF glass, which is hydrofluoric acid resistant. There's not as much call as you would think in bioprocess for HF required, but if you are doing something that has HF as part of it, this will not stop the probe from dissolving in the HF over time, but it will give it some resistance. So all of the glasses have different reasons for being. Okay. There's also different forms of pH glass. Now, this is much more specific to laboratory probes than process probes. Okay. Solutions tend to have a round bulb, which is why we use them in bioprocess. There are flat caps. Those are really great to get surface measurements. So paper, skin, leather, where pH can be very important in the processing. Meat and cheese have a pointy tip, so it can penetrate into the layer and get you a measurement just below the surface. And they all have different reasons. Again, in biopharma and bioprocess and in labs, you're going to generally see the round bulb. All right, the next thing that we're going to talk about is liquid junctions. They're really important. You need that flow of ions to go from within the reference to the solution to form that circuit. If your liquid junction is clogged, then you won't get a good reading or any reading at all because you've broken the circuit. It's a broken electrical circuit. So there's two types of junctions. There's double junctions in probes and single junctions. Single junctions are less expensive. They have a bad habit of letting your sample ingress inside the probe. So you can get a poisoned reference very quickly. They have shorter lifetimes for use. And anything in bioprocess needs to be what's called a double junction, where if you look at the double junction, here's your junction, and your reference is actually isolated behind another junction. So there's an outer junction and an inner junction. So all of the bioprocess probes that you're going to use if you're using a bioreactor are going to be a double junction, and the best laboratory probes you can use should have a double junction. So if we think about single pore junctions and ceramic pore junctions, there's reasons for both. And these are the two most common junctions found in bioprocess or in laboratory. A single pore is just a hole that's been drilled so that the electrolyte can move ions out into the process. They're great because they don't clog. They're really good if you have dirty samples or samples that are really chunky. They're pretty low maintenance, but they are a shorter lifetime than a junction that has a barrier. Ceramic junctions, which in Hamilton probes, they're called coatramic diaphragms. And I'll show you an example of this. This has a ceramic plug in here. It's a great physical barrier. It's sterile. It prevents your process from entering into your probe. In addition, this is generally coupled with a pressurized or viscous electrolyte that also presses and pushes out so that your process does not enter into your probe. So let's just take a brief moment and look at a couple examples of that. On this probe, if you look at the electrolyte, if I turn it upside down, it moves very slowly. It's a thickened viscous electrolyte. And if you look, you can see a white dot. That's the coatramic junction. It's a ceramic barrier. If we look at our polymeric probe, this happens to be a broken one, just for your own information. The glass broke and I managed to steal the probe so I could show you what a polymeric probe looks like. But this inside is completely solid, or it's polymer. It's not going to flow out. And if you find the junction on it, it's actually a glass hole right there. It's just been drilled through. So those are two different kinds of commonly used junctions. In laboratory probes, there's a third kind of junction that you might see. If you see it, you should not be using it if you're using biosamples. And that's called a wick junction. They look a lot like this. This is an image from Thermo Fisher. There's reasons for these probes, but they should never be used in bioprocess. But they have glass fiber or fiber optic bundle or some sort of dacron internal in here that wicks the process up into the sensor. These are really prone to clogging. They cannot deal with dirt, and you can't really clean them, which means if you're measuring biological samples in them, they can actually grow on the glass fiber and contaminate the probe. So it's very important, if you have a wick junction probe in your bioprocess, that you stop using it for any of your biological samples. There are good times for that. Basic, simple aqueous samples. If you're doing basic chemistry, they're great for that. But they were never designed to be used with biologics. We're going to talk a little bit about the silver chloride reference system, okay? Caveat first. Silver plus protein makes a big, ugly, insoluble mass of black particulate. It's possibly the worst thing we could use in biological, except that it is the best thing to use for pH reference. So all references in pH electrodes tend to be a silver chloride based. Because our samples make proteins, proteins plus silver equals a nasty black mess, we have to work really hard to make sure that we isolate our reference system from our process, because we don't want that silver going out into the process. So basically, most reference systems look a lot like this. Slight differences. Your liquid junction, outer junction is here. Okay. Then we have your reference electrolyte, which is some sort of buffered potassium chloride usually, or silver chloride solution. It's a potassium chloride. There's a diffusion barrier. This is that double junction because you have to get through the second junction. Diffusion barrier's entire job is to capture proteins and silver before the proteins can get anywhere into the wire. And inside here is where your silver chloride solution is with your silver wire. Okay, it's basically what it looks like, so that you get no leakage of the silver chloride solution out into your reference, and from there out into your process. And again, every manufacturer has their own special version of doing this. Hamilton has two, and they're both called the EverF reference systems. The first is in our polymeric. Remember that pink probe I just showed you? In that probe, what you end up having is the polylite here. You have that open single pore here. Your ions have to, if your process was going to enter in, it would have to climb up a solid polymer matrix all the way up here, because they put their reference upside down. Then it has to crawl all the way down to get to the silver chloride wire, which is right at the end. That's about 200 millimeters of motion that the process has to go. It's a long ways, and it's a pretty darn good way of preventing contamination of the silver chloride with protein. In the EverF, or the EasyFirm Plus, which is our primary process probes used in biologics, we have the coatramic ceramic junction here, and we have a thickened viscous electrolyte here, just like a potassium chloride electrolyte. The process has to enter through the first junction, go down, go through a second junction. There's a lot of things going on in this. There's a diffusion barrier that traps proteins. Then there's a silver scavenger just in case. Then there's a second diffusion barrier, and then behind all of that is your silver chloride. So it's very difficult to actually get penetration of your process up into and contaminate. And you can see this from the outside. And if you start seeing little specks of black showing up in your silver scavenger layer, it actually tells you that your probe might be getting towards an end of life, because these are consumable probes. Okay. There are three basic main categories of pH probes then. And for this, I'm talking about both process and laboratory. There's a probe where your electrolyte is under pressure. Typically, those have some sort of barrier in place. The second kind is where you have a single pore junction, and you either have a polymeric solid electrolyte, or perhaps a refillable. And the third is a refillable reference, where you're constantly adding more electrolyte into your pH probe. In the pressurized, our EasyFirm probes are one example of it. These are great probes. They have a ceramic diaphragm. You have a thickened viscous electrolyte. They're maintenance free. You have a sterile barrier with the ceramic junction. They're autoclavable. They can do SIP. They can do CIP, clean in place, steam in place. And they're really heavily used in biotech, pharma, food, and beverage. A polymeric version is also pretty maintenance free, but they're really good for wastewater, chemistry productions. I've used them in some food, but generally not so much because their electrolyte is not considered food grade. And then there's refillables. The one I'm showing you here would never be used in biopharma. It's really specifically used for heavy chemistry or mining. But the reason I show you it is because it clearly shows you a refill port and a simple probe, and probably 2/3 of the laboratory pH probes that you might use in your labs are refillable electrolyte probes. Now, at least some of the most commonly used ones. So with all these sensors, it's really important that you start thinking about choosing the correct sensor for your process. And there's a lot that can go into making that decision. When you're looking at that decision, one of the questions you have to ask is, what's your process? Is there something that is happening in your process that might require a special kind of glass? Is my process particularly chunky and dirty? Can I use a ceramic junction, or do I need to use an open junction? What kind of electrolyte do I need? Now, one of the only things you might be really thinking about in bioprocess is, do I need a food grade electrolyte, or do I need a non-food grade electrolyte? In other words, do I care if I have food grade? If you're working for companies like Finless, Impossible Foods, Perfect Day, and you're making samples that might actually be consumed, you're going to want a food grade electrolyte. So you need to make sure that your sensor will work with that. And that's in case anything happens. Also, they just like to know that you used food grade in everything. But if you don't care, then you don't need a food grade. Glass type. Am I making anything with HF? Am I making anything that forms biofilms? Do I need to consider any of these processes? Electrical connections are huge, and we'll talk about those more in just a minute. What sort of precision do you need? Are you okay if it's plus or minus half a pH unit, or do you need to really knock it down to 0.05? What kind of maintenance do you want to do on a daily basis? Do you want low maintenance, or do you want to have to do high maintenance? And when you're talking about pH probes, maintenance does not take into account calibration. Just get over it. You have to calibrate pH probes all the time. When we talk about maintenance, we talk about, am I having to spend time refilling that electrolyte? Am I having to spend time cleaning the chamber with the electrolyte in? And what sort of lifetime do you want for your probe? There's a range of probe lifetimes for process probes. They can last anywhere from a single use all the way up to maybe about 9 to 12 months. It is rare for any process probe in biologics to last more than 9 to 12 months. More often they last about 3 to 6. It depends again on what you're doing. There's a lot of things that impact that. So this is just sort of some of the Hamilton ones. If you want to go on our website and look so you can get an idea of what the differences are, there are spec sheets on all these you can look. But in laboratory probes, we have a ceramic junction with refillable. We have single pore refillable. We have polymers with single pore. And in process probes, we again have all of these different kinds. Sometimes people find it a little interesting to just look and see what the differences between those probes are. So you'll have access to this information. In laboratory pH sensors, it's really important to understand the sensor connector. And this really has to do with what you're connecting to. You'll have a pH meter, and then you need a pH probe to go to it. And you'll connect your pH probe through a connector like this. Depending on your probe, there will be some sort of connector at the end. And you need to put your connector here. And then you need another connector that goes into your pH meter. And understanding what those connectors are is important. So their most common ones are either BNC connectors. There's a female, there's a male, or sorry, male, then a female. There are 3.5 millimeter pin connectors. Those are also called single pin, or DIN connectors or DIN quick connects. DIN quick connects have some interest in some facilities and use because it's a threaded connection. So it gives it a little bit more of a waterproof, secure connection than some of the other connectors. In process, this is going to depend on what your bioreactor requires. All of these are standard connectors. An S8 and a K8 are really good for autoclavation and sterilization. They're also a much older form of connector. The K8 are still used, the S8 are less used. VP6 has temperature compensation, but it's not what's called a smart probe. It's still an analog sensor. MemoSense is what's called an intelligent sensor. It has some feedback. It has some external things you can do with it. And then in Hamilton, we call our top of the line sensors, the intelligent sensors are called ARC sensors, and they can give you a 4 to 20 signal out, a Modbus signal out. They have actual software and Bluetooth connections, so you can get dynamic troubleshooting and a lot of information off the probe. So it just depends on what you need for your process. There are some common experiences when I've talked to people around the Bay at different biotech companies that they've experienced. One is that their laboratory probes might provide a very different pH measurement than their inline process sensors. That's not really good, because the ideal world is you have an inline sensor, it's measuring pH all the time, and you take a grab sample and you mark the time on your inline sensor and you go and you take a measurement. You're hoping that they match. If they don't, that means either something's wrong with your inline sensor, something's wrong with your offline sensor, or something happened wrong in your sampling technique. You really need to understand the difference. Laboratory pH sensors are often considered to be the standard. So you might measure in your process with your inline sensor, and then you measure an aliquot offline, and you might do an adjustment because you say that your offline laboratory pH probe is the standard accurate probe. So you tweak your information on your bioreactor sensor and say, nope, I'm going to match the offline. There can be some challenges in doing that, because if you don't calibrate your laboratory pH probes the same way you calibrate your process probes, if you don't do maintenance and cleaning and all those other things and treat those laboratory pH probes as precious as your inline, you can lead to some differences in performance. So you might not be doing an accurate comparison. And sometimes, more frequently than most of us would like to hear, people can't tell me why they selected their current laboratory probe. We've always used that one. Well, the sensor rep that I bought from the catalog sales rep said that I should use it, or it was the least expensive pH sensor in the catalog and we're on a limited budget, so we grabbed it because it was the cheapest. It's really important to understand your laboratory sensor if you're going to use it as a comparison to referee your inline. So you should know what kind of sensor it is. You should understand why it was selected. Your catalog sales rep might be a pH expert, or they might just be somebody who represents an entire catalog of thousands of parts, and they're going to pick the one that is the one they're familiar with or the one that gives them the most commission. They may not know why you should pick it. So we're going to talk briefly about pH calibration. pH calibration is all about understanding temperature and accuracy and best practices. But before we even go into the practical side of things, we're going to do an exercise on how to calculate the pH slope. So if you've ever looked at your laboratory probe, and say you have a laboratory meter that's pretty smart, and you do a quick calibration, it may be a pH 4 and a pH 7 buffer, and you get a little printout on your thing that says the slope of your pH is this and the offset is this, and you write that down and you keep notes in it. How is slope calculated and how is offset calculated? Okay, this goes back to something called the Nernst equation. If you think way back to school, depends on what school you've done. It might have been high school chemistry. It might have been undergrad. It might have been graduate school. The Nernst equation is an interesting equation. So The Nernst equation basically tells you that for every change in pH at a specific temperature, and the example we're going to use right now is at 25 degrees Celsius, every change from one pH unit to the next has a difference in voltage of 59.16 millivolts. Okay, so that means if I measure signal at pH 7 and I measure a signal at pH 8, there should be 59.16 millivolt difference in that measurement. Okay, so let's just do an example. If we were to read on our pH meter a measurement at pH 7 in a buffer, a good clean buffer that we're confident in, and let's just say the reading we get is minus 7.4 millivolt. Okay, well, one would think at a pH 7 it should be 0, right? Hydroxide ions should be equivalent to hydrogen to hydroxide. So it should be neutral, but minus 7.4 is acceptable. And then we take a reading at a pH 4 buffer, and we get a reading of 164.6 millivolts. That's, for all intents and purposes, 3 pH units. Okay. And if you take 164 and you subtract a negative 7.4, you get a span of 172 millivolts across 3 pH units. But the Nernst equation says that it should be 3 times 59.16 millivolts, which is 176.9 millivolts. The slope is the actual measurement divided by the theoretical, which gives us a slope of 97%. Okay. We're going to talk about these min-maxes in just a minute, but keep them in mind. So ideally, your pH readout should look a lot like this. At pH 7, you should get 0 millivolts, and there should be exactly at 25 degrees, 59.16 difference in pH or in voltage between each of these units. The reality is an ideal sensor doesn't really exist. And as you use a sensor, things change. So maybe you measure your slope and you get a slope of 80. What does that mean? 80 means it's time to change and replace your pH sensor. Its slope is too far out of appropriate to give you a good measurement. Okay? Slope is all about the condition of the glass electrode, not the reference, the measuring electrode. So if your slope is off, that means your measuring electrode with that pH glass and everything isn't as good as it should be. Something has aged in it, something has changed in it. You can't fix it once that changes. The offset that you've gotten, an offset is how different at pH 7 are you from that ideal measurement of 0 millivolts. Okay, so say you have two measurements and you got a slope of 98 for both of them, but you get an offset on one of them. You see at pH 7, your ideal should be 0, but you're getting something different. Maybe you're getting minus 10 millivolts. Maybe you're getting plus 10 millivolts. The offset is all about the condition of the reference electrode, not the measuring. Okay, what's included in the reference? That's the junction, that's the reference electrolyte, right? That's the silver chloride reference. So something has changed in that side of it. Now, we'd said on that first slide a couple slides ago that if you're not plus or minus 40 millivolts at pH 7, your electrode will fail. Basically, if your offset is more than plus or minus 40 millivolts at pH 7, that sensor is non-recoverable and needs to be thrown out. It means the change has happened so significantly to the reference side that the probe is not retainable. Almost 80% of all pH failures are due to a failure in the reference electrode. Okay. So let's talk for a minute about best practices with calibration. You should always calibrate with 2 buffers, and you want the best buffers that you can have. I was at a lab before COVID hit, and I was allowed to take this picture of buffers that were on the shelf. And if you look at this, you're going to see there's a brand new, beautiful bottle of pink buffer, and then there's an opened one that kind of looks like purple. Then there's a bright yellow buffer, And then there's one that kind of looks like a yellowy, muddy green. These two center ones are the ones that they were actively using. And I asked them, I said, you know, those buffers are not the right color. Oh, we just shake them up. Don't worry about it. They're fine. They're not fine. The color of your buffer is really important. It's an indicator. The worst case was, and they didn't let me take a picture, I saw one buffer that was almost as full as this, had been open for a while, and it was a bright pink on the bottom and a dark purple on the top. And there was a full gradient in between. And I asked them what they did. They said, oh, we just shake it up, make it one color. It works fine. The answer to that is it doesn't. You want two buffers, and you want those buffers to be the best buffers you can. There are different manufacturers of buffers, but if the color is supposed to be a bright pink or a bright green, it's an indicator. It needs to be the same color as an unopened bottle. If it isn't, it's time to change to a new bottle of buffer. Buffers have lifetime. When you first get a bottle of buffer, you should write a receive date on it. And when you open it, you should write an open date. And there should be an expiration date on your buffer. Okay, in this case, it's, I don't know if you can see it, but it's 01/26/2024. So when you get buffers in your lab, you should actually have sort of them cataloged. And at the back end should be your oldest buffers that were received most recent that have the latest expiration dates, and you should work your way through. But you should always manually mark when you received your buffer and when you opened it. And when you, before you even label it, you should always check the expiration date to make sure you got the best buffer. Okay. Buffers should be as important to your decision as the media you're using, as the every single thing you're putting in your bioreactor. Buffers are as critical as all of those. Okay. So just a very brief overview of that. Oops, too fast. Don't use buffers that are wrong colors. Do check the dates. And you want to use clean buffer every single time. So there's a lot of different kinds of buffer bottles out there. Hamilton has a really kind of cool one. You don't want to have conical tubes filled with buffer floating around your lab with probes sitting inside of them. You should use fresh buffer every time you calibrate and every time you validate. In this case, the Hamilton ones are super easy to use because if you just squeeze, it fills a small amount of buffer into this cup. There's a valve in here that prevents it from going back in, and it only goes up one way. It doesn't come back. And this means I have a handy dandy way of measuring fresh buffer every time I need to measure. And when I'm measuring with fresh buffer, I should always rinse my probe before going from one bottle to the next and blot and then put it in. And here's my buffer. When I'm done with that, I rinse, I blot, I put my probe away. Then I should throw my buffer out and use fresh buffer next time. If you don't want to use something like that, or your buffer bottle does not have cute little cups, then you may want to do something like put it into a beaker or a conical tube, but fresh buffer every single round. Okay. These are considered best practices, and some people have challenges with it because that means it can be a little more expensive. And cost is important, but losing an entire process because your pH is off is more expensive than buying a bottle of buffer because you need to replace it. When you're calibrating with buffers, you want to make sure that your buffers for calibration are no more than 3 pH units apart and no less than 2. Okay, so you also want to make sure that the buffers bookend your process. So if my process is a pH 7.6, is a pH 4 buffer and a pH 7 buffer a good choice when I'm doing my calibration? Just pop your answer in the chat window. My process is a pH 7.8 or 7.6, and I'm thinking about calibrating with a pH 4 and a pH 7 buffer. The answer is no. I'm not bookending. I need to do something that's between. Correct. Doug suggests that maybe I use a 7 and a 10, and that works because my target range is right in the middle. I want to bookend my buffers. Okay. Now, there's some really weird pH units out there. I think we're all used to 4, 7, and 10, but believe it or not, there are buffers for pH 1.68, pH 3.5, pH 8, pH 5. So you can get that 3 units by playing around with those buffers and getting an idea. When you do a calibration, you should measure your sensor in your first buffer, rinse, blot, measure it in your second buffer, and calibrate, because you're going to calibrate at both points, and then rinse, blot, and then go back to your first sensor. You want to check it within 60 seconds. Let's just say, for an example, you go 4 and 7. Go from a pH 4, calibrate at pH 7, go back to the 4. In 60 seconds, your probe should come to a stable pH 4 measurement. If it cannot do that in 60 seconds, your probe might not be good or it might need to be cleaned. Once you're at pH 4, it should stay stable with no drift for several minutes, as long as your temperature is stable. If your probe is going all over the place, your probe might need cleaning. So a best practice is every single time you calibrate at 1, calibrate at the second, go back, verify in the first, and then verify drift. Every time you calibrate your probe, you should keep a log of the slope and the offset. We'll talk in a few minutes about how often we calibrate, but there's a couple other things I want to talk about in calibration. When you're storing your pH probe or you're putting your probe in something, you should never rest your probe so that it is lying down, on the bottom of something. It should never be sitting all the way to the bottom. It should always be up in the air, surrounded by liquid. That means you should never sit it in a conical tube, hanging out, just sitting in the bottom here. If that glass is resting on the bottom, it does things to the gel layer. It deforms it. And if that outer gel layer gets deformed, then you can get errors in measurement. Okay? So again, you always want your probe suspended by liquid on all sides, not resting that bulb. Storage in conical tubes where it's resting is not a good choice because that causes deformation. When you're measuring in buffers, you should not just stick the probe in the solution and let it hang out sitting on the bottom, because that can deform that gel layer and cause some problems. Okay. When you are rinsing and going from one spot to the next, you're going from one to the next. Again, always rinse your probe with some DI water. And then you want to blot. You never want to scrub or rub down. You never want to rub the end, because that can scratch that gel layer. And if you damage that gel layer, that's one of the ways you can damage the measuring side. And that can have an impact on slope. Okay. These probes should be stored not in buffer, but in storage solution. And they always come with some sort of what's called a watering cap. Okay. Different probes, watering caps may look a little different. This is the watering cap for a process sensor. If I look at my laboratory sensor, this is the watering cap. It's quite long. They'll all have some sort of watering cap. There's some ways that you handle watering caps. They should be screwed on. They should be filled with storage solution. What you should never do is pull this out and hear a pop. That's bad and can cause problems because the pressurized electrolyte inside can be pulled out through the liquid junction, and it can help depressurize that electrolyte, When this gets depressurized, the process can go in. On the same side, you shouldn't try and push it in here. If the cap's too tight because it's pressurized, unscrew the cap so it's nice and loose and slide your probe in, lift it up so it's not on the bottom, and there you go. Okay. Calibration and handling best practices. Track your slope every time you calibrate. Track your offset every time you calibrate. How often do you calibrate? Well, that's an excellent question. I'm glad you asked me. It depends. If you're a process probe that's going in a bioreactor, you will calibrate when you're finished every run. So at the end of a run, you will clean your probe, you will calibrate it, and then you will set it on the shelf so that the next time you need it, you can put it in the autoclave, and then you put it in your bioreactor and you go. So after every run. If it's a laboratory probe, you should calibrate at least once a day. Why do I say at least? Because it depends on the number of samples you're running. If you're only running 1 or 2 samples, once a day is probably going to be accurate. If you're sitting there at a bench and you're working for somebody and they have you sitting there doing calibration or measuring sample after measuring sample for 6-8 hours in a row, you might want to check your system midway. Instead of calibrating automatically after so many samples, you may want to take your electrode, rinse it, blot it, and place it in a buffer to see, does it get to that buffered measurement within 60 seconds? And is it stable? And is it accurate? If it fails any one of those 3, accurate, stable measurement in 60 seconds, no drift, then your sensor needs to be cleaned. And if it needs to be cleaned, then you should always recalibrate after. So many companies will have a process that best practices suggest that every X number of times you take a measurement, you do a validation or a verification. If it passes, you can do that many measurements again. If it fails, you clean, calibrate, and do it again. And you should keep the log of every time it changes. Okay. Your sample type is really important on this. If you are working with some biological sample that has a bad habit of leaving biofilms or coating things, you're going to have to clean your probe more often. You won't get as many samples before cleaning. If your slope is greater than 85 and less than 102, your sensor's in good shape. If your probe started at 85 or say 90, and at the end of all your samples is still at 90, you haven't had a big change in that, that's good news. If it's outside of that range, you need to clean. And if cleaning doesn't fix it, you need to replace it. There are some experiences in some people that have what's called critical pH. If their critters experience less than any tiny change in pH, 0.1, they could get a huge dramatic change in titer or viability. The example I gave you earlier was a 0.3 difference in pH unit resulted in a 50% increase in titer. That's what we would consider a critical pH control. You don't want any shift or any problems. In those cases, people tend to use a much tighter slope range, and they'll only accept probes that work between the 95 and 102%. And some people in large biopharma projects where they're manufacturing will actually use a pH probe only once. So they will get it, they will calibrate it, they will autoclave it, they will use it one time, and then they will throw it out because they don't want to deal with the cleaning, the risk, the contamination, and any of the problems. Okay. Temperature has a huge impact on pH. We already talked about that. It impacts pH by increasing the dissociation of ions, which increases the activity, so therefore it affects pH. But there's one delightful point called the isopotential point, where a change in temperature has no change on the pH. That's wonderful news. The temperature will change with the calibration slope. So if you look at this example graph, temperature changes slope. So at 100 degrees, the light green, you can see it has this slope. Red is at 50 degrees and blue is at 0. There's a very different graph. This is why sensors need to have temperature compensation. The point at which there's no change is the isopotential. In theory, that should always happen at pH 7, because at pH 7, you should have the same concentration of hydrogen ions as hydroxide ions, therefore there's no change. Temperature has more of an effect than just the isopotential or the slope. It can affect the electrode itself, it can affect your calibration, it can affect your buffers and your samples. Okay, so there's some best practices there. Best practices suggest that you should calibrate your sample and your buffers all at the same temperature. Okay, so what that means is you've got a bioreactor and you take a sample, you take an aliquot, and it's at 36 degrees. You should have best practices done all of your calibration and your buffers for that sensor at 36 degrees. Even though there's compensation, you're trying to reduce any potential errors that are brought in from that. Now, that's not always practical. It's delightful for me to say that you should have a water bath or some sort of temperature controlled bath that's exactly at 36 degrees sitting on your bench at all times. And you can have that filled with little beakers of storage solution. And you can put your buffer in there and make sure it's equilibrated at 36 degrees so that when you do your calibration, everything's at 36 degrees, and you'll store your probe in storage solution in the calibration thing at 36 degrees so that when you go to do your buffer, you rinse it into waste, you put it in, your probe, all the glass is at 36 degrees, your solutions are at 36. It'll come to equilibrium very quickly. If you take a sample, you pull it out of your bioreactor, you immediately put it into your sterile thing in the water bath so that it's at 36 degrees. It's a lovely sentiment. And it's not done as often as it probably should be. But that is one way of doing a truly good temperature that avoids requiring compensation, and it avoids any errors from compensation. Having a pH probe that has built-in temperature probes is actually very helpful. Now, the probes that are built into a bioprobe or into a pH probe should never be used to control your entire process on. They're not that accurate. In fact, many bioreactors will have a single RTD probe that's in your bioprocess that controls the temperature of your entire process, and they will actually use that temperature probe to compensate your DO probes, your pH probes, and any other measurement analytics you have in there, instead of using any of the onboard temperature measurements within different sensors, because it's more accurate. Okay. Buffers actually have different pH at different temperatures. Go figure. Newer laboratory meters might have a temperature chart built in, and they might have it in for different manufacturers. So if you tell your pH meter that you are using a Hamilton buffer, it might have that data built into it. If you're using a BWR buffer, it might have that data built into it. If not, you might need to put that data in there. Here's just an example. If we look at, say, a pH 10 buffer, at 0 degrees, it's 10.32. At 30 degrees, it's 9.97. That's a pretty significant difference in pH, so you need to use the correct value for the correct temperature. Where do you find this information? Well, there are tables, and every manufacturer has the ability for you to get that information. But you can actually find a limited version on the side of your pH buffer bottle. So this is off of my pH 10 bottle from back there. You can see at 5 degrees, it's 10.19, at 10 degrees, it's 10.15, and so forth. That's only every so many degrees. It's not even uniform. These are at commonly measured 18 degrees, 20, 22. These are at common culture sort of things. Again, there are tables. There are detailed tables for a lot more information. So you just need to know. Okay. Care and maintenance. When do you need to clean a pH probe? And this is the same for laboratory probes and process probes. Check your slope. If it's outside of that 85 to 102, you need to clean it. Check your logs. If you finished the last time you calibrated this probe, it had a slope of 87. And this time, or say, okay, let's do more dramatic. It had a slope of 97. And you did a bunch of samples, and then you went back and you did it again and at a slope of 84. That's a huge drop, 97 to 84. So that means something happened to that probe during its usage. Maybe it got a coating, maybe something got scratched, maybe it got banged up, maybe something contaminated the reference. So you need to try cleaning first to see if you can recover it. Because if you just did a few measurements and you come back and it goes all the way back up to 97, that's fantastic. If it doesn't, that gives you an idea that there's something else going on. Maybe it's no longer any good. Once you have a clean probe, or you're not sure, it was 97, it's 97 again, and you do the 474 example and you check your stability in the buffer and it does not come to that pH 4 in 60 seconds. In fact, it takes almost 10 minutes. First, ask yourself, was this pH sensor sitting in the refrigerator at 4 degrees and my buffer was at 36? Because it's going to take some time for the temperature of this glass to equalize to the temperature of your buffer or your measured sample. So as long as they are at a thermal equilibrium, then 60 seconds. And if it doesn't, that means your buffers or your pH probes moving slowly. Slow responses tend to be an indication that there's a problem with your liquid junction. It might be getting clogged. How accurate was it to pH 4 when you went back? You just calibrated at 4, then you calibrated at 7, you go back to 4 and oops, it's reading 4.6. Well, you just calibrated it. So if it can't read what it just did, this is an indication that you need to clean your probe. A really good best practice for verification is to use another pH buffer that's between the two outlanders. So you calibrate at 4, you calibrate at 7, and you have a bottle of pH 5 buffer hanging around just for verification. And so you put the probe in the 5. You're in the middle of your range. It should give you a good reading. And then again, if I leave that probe in the solution, does it stay stable or am I getting drifting and noise? Okay. How do you clean a probe? Well, you clean a probe by using cleaning solutions. Every manufacturer has their own. I recommend you use the one that the manufacturer of your probe suggests. If they don't have one, Hamilton has a really good line. There's some generic ones out there and you can make your own buffers. It just depends on your time and constraints. So generally speaking, at the end of a run, especially bioprocess, sometimes in the lab, you should take your electrode out of your process, rinse it off so there are no chunky bits floating on it. There's no debris, no cells, anything like that. Soak the probe in a cleaning solution for 30 minutes. Hamilton has a cleaning solution A, a cleaning solution B. The A is for cleaning if you have acidic, if your probes were exposed to acidic solutions. It's actually a basic solution, so it helps offset. The B is cleaning if your probe was exposed to basic solutions. So was your culture in the basic range. Leave it there for 30 seconds or so, hanging out, floating, not resting on the bottom. Then rinse it with DI water and soak it in storage solution, which is just a 3 molar KCl, for 2 hours minimum. That soaking is required to rehydrate the gel layer and to rebalance and re-equilibrate everything. If you're getting a really slow response, then it could be your junction is clogged, and that is how the ions move out of the junction and go to the bulb. If it's clogged, you'll get a slow, sluggish probe. You might need to put the whole probe, just the end, measuring end, in a 0.1 molar HCl solution at 70 degrees Celsius for 15 minutes and have that solution stirring. Rinse it really well with DI water and then put it in your storage solution for 2 hours before taking measurements. Again, you need to rehydrate and re-equilibrate. If your solution is bad at leaving deposits, protein buildup, biofilms, then you might need to soak your electrode in a solvent that will remove deposits. Pepsin is a good solvent, is good for protein removal. Bleach can remove certain deposits of things. Again, keep it dilute and then rinse it with water and soak it in KCl in the storage solution for 2 hours. If you're not sure if your junction has been cleaned after that, if you lift your sensor up into the air, remember that white ceramic junction I told you about, you leave it hanging out for about 10 minutes, you should see a little bit of powder showing up around that junction. That's actually a good sign because that means you're getting slight ions moving out and it forms as a KCl powder. It's not going to harm your bioprocess, but that tells you you're getting that ion exchange, and that's a good, healthy probe. So how do you measure properly? What is the best way in the world to take a calibration measurement or a sample measurement? Well, first, you should have a stirring plate. You never want to measure pH if you're not consistently stirring, okay? Stirring plates will often add heat. So on my stirring plate, I have a thick foam that prevents heat transfer from my plate up into my solution. There are varying versions of that. There are insulating pads. If you have a heating stirring plate, you make sure that the heat is off during this. You want to make sure you're stirring. You need to keep that solution continuously stirring throughout the process. If you're not stirring, you're not going to get a good result. Okay. Make sure your sensor is in the middle of the solution. It's surrounded. It is not resting on the bottom or anything like that. You want it surrounded by liquid. When the system has had time so that the liquid and your probe and sensor are at the same temperature and they've had time to equilibrate, you can look in your software. I happen to be using the Hamilton Arc Air software, and I can see that my probe, if I look in it, is measuring 2.98 pH, and the temperature of my solution is 21.99 degrees Celsius. I can actually see all sorts of information about this probe in the software. This is one of our intelligent probes. I told you it gives you a lot of information. One of the cool bits of information that it gives you is a quality indicator. This is sort of a mathematical calculation combining the slope and the offset to tell you if the probe is good and whether it should be replaced or not. So in this case, it's 100% because my probe's in great condition, and it actually tells me my operating hours. I have 808 operating hours in this. It'll tell me its highs and lows and all of that. The software also has a great calibration wizard, and you can put in your lots. You can actually scan with a barcode scanner if you wanted to do that as well. But that's not what we're looking at here. What we're looking at is I have a pH of 2.98, which is good because this is just vinegar in water with a hint of blue food coloring, so it showed up. So it should be very nice and acidic. Anyhow, you're stirring. If you're going to move from one to the other, again, as you move up, you lift your sensor up, you rinse it with DI water, you blot at the end, you move into your next location. These are all important things. So the keys to accuracy: always use fresh buffers when you calibrate. Always, always, always. Okay. Verify the expiration dates before using every time. It should just be part of your SOP. Also check and see how long your buffers have been open. Buffers have sort of a lifetime separate from their expiration date once they're open. Hamilton's buffers last a tremendously much longer time than any other manufacturers because we add a crazy amount of extra buffering capacity. But typically a buffer is good for roughly 2 to 3 months after opening, as long as the color is good. If it's a pH 10 buffer, you've got roughly 3 to 4 weeks from the time you open it to the time you need to throw that bottle out. The CO2 in the air actually causes a shift in the pH of your solution and your buffers over time. So if you do not have enough buffering capacity, your buffers will go bad quickly and the color will change quickly. Hamilton actually suggests that your buffers are good for 1 year after opening, but again, check your colors. Also, if you don't rinse your probe from one solution to the next, and you're actually putting your probe in your buffer bottles, you can contaminate your buffers, and so you may need to replace them more quickly. These should be considered stock solutions and always poured into another container. When you are calibrating with buffers, the same thing as you saw with my beaker, you should pour the buffer into a small beaker, have a stir bar, and be stirring while pouring. If you choose to measure in a buffer bottle, then you will actually watch me shake my buffer bottle. I don't know if any of you remember way back to titration in school, but remember when you were titrating, you would always stir or shake your solution below because you wanted to maintain equilibrium. Same thing applies when you're measuring pH. Always stir. If you have a refillable pH probe, now this is specific for anything in bioprocess to laboratory probes. You need to make sure that you refill the electrolyte in the probe. So if you have a laboratory probe, you're going to notice if it's refillable, it'll have some sort of plug. Okay. When you're taking measurements, you need to make sure that plug is open, because the liquid needs to be able to flow down so you get that ion release into the solution so you can get a measurement. If you have it plugged in, it's like a straw. If you put your thumb over the end, no ions will flow, no liquid will flow, your measurement won't work. Once a week, you need to dump out the electrolyte that's inside of your probe. Do a quick rinse with some DI water in there. Do a quick rinse with some electrolyte, and then refill your probe to the correct fill line with electrolyte. If you're doing a lot of measurements, you may need to check this midweek to verify. For storage, put your cap on to plug it away. If you have a refillable probe, okay, you need to make sure you use the correct electrolyte for your sensor. This is one of those few times that I am a brand person. If you buy a probe from any manufacturer, they will specify an electrolyte for that specific pH sensor. If they have 25 different sensors, they may have 25 different electrolytes. But when they made their probe and designed it, they designed it to be used with a specific electrolyte, a specific type of glass, a specific type of junction, and to work together. If you put any other electrolyte in that sensor, they will no longer guarantee the performance, the accuracy, the results. But you need to make sure you use the correct electrolyte for your manufacturer for the probe. Okay. When you're measuring pH or calibrating, it's the same basic process. And we already talked about this a little bit. Gently stir your buffers and your samples. When you move your probe into the sample, let it sit for a couple minutes for the temperature to equilibrate before measuring. Specifically on refillable probes, especially after you've refilled it, you may notice that there are some air bubbles in your electrolyte. So you may need to shake your probe down to get rid of air bubbles, because air bubbles will alter your electrical circuit and change your connections. Okay. I already talked about using insulation. And blot your electrodes between samples. Never rub that bulb. Storage. How do you store pH probes appropriately? Never, ever store probes in distilled water or in tap water. It's not a good thing to do, and it will shorten the lifetime of your probe dramatically, if not irrevocably. Think about the gradient. Solutions want to go from high gradient to low, and water, distilled water, has no ions in it at all, so it's going to draw reference electrolyte out and eventually kill your probe. You should never let your probes go dry. Now I say that. And they should always be stored in storage solution, which is a buffered 3 molar KCl. But there are some situations in some laboratories where you might be forced to autoclave your sensors dry because your autoclave is not big enough for your sensors to be in your bioreactor with all the sensors in, possibly filled with media, to go into the autoclave. And if your bioreactor is not large enough and you have to autoclave your sensors separate from your glass and then in a sterile hood put them together, well, once you add the media back in, you need to let your pH probes hang out in the media, re-wetting for 2 to 3 hours before you can get accurate, good, stable measurements. Because that liquid gel layer has dried and it needs to rehydrate and it needs to reform and it needs to stabilize. So it can take a couple hours. Also, drying your probes continuously can result in a shorter lifetime. They tend to be a little more sensitive when they're dry. So if they get banged around, again, that outer gel layer is a little more sensitive. Okay. Do not store your pH probes in buffer. It's just not a good choice. We're going to briefly go over intelligent sensors and some of the cool things and a troubleshooting checklist, and then I will take any questions you guys have. So, troubleshooting, because things happen. Sometimes when you're taking measurements, you will see something like the graph you see here. Maybe your readings are not reproducible. Maybe you're getting really slow response. You just added a whole lot of acid into your bioreactor and nothing is changing at all. Okay. Your response is super, super noisy, or you're not getting any accuracy. When you look at this graph, the black lines are actually from offline measurements, the black dots, and the gray and the green are your online measurements. So they just did best fit on the black dots. And look how noisy it is, and it's drifty and they don't match. This is room for anxiety and a little stress when you're doing bioprocess. So there's a troubleshooting sequence that happens when you're calibrating or when you're measuring and you're trying to figure out where your problems were. The first is check the buffers that you used. Are they the right color? Are they within date? Do they blanket where your expected pH range is? Are they expired or not? Then check your reference electrode. How do you check your reference electrode again? Remember, that is checked through the offset. How far off of 0 is your offset? Is it within that plus or minus 40 millivolt range? Then check your pH electrode, the measuring electrode. What's the indicator of that? Your slope. Are you above 85 or below 102% slope? Did your slope change a lot from the last time you took a measurement? These are, again, big indicators. This is why keeping a log is really important. Then your sample. How was your sampling taken? Did your sample sit out in the open air for a long time between the time you took it and the time you measured it? Because CO2 from the air can impact your sample. Was sterile measuring done? Is there any potential that contamination happened during that? Because contamination can also impact your pH. Then finally, consider your technique. Are you stirring? Do you have temperature isolation with your mixing plate? Do you have, are you rinsing? Are you blotting between? Are you cleaning? Have you checked the cleanliness of your probes? Again, this is sort of a list that I just talked about, all of the things. If you're getting sluggish response, check the liquid junction. Are you getting precipitate? Does it need to be cleaned? At the end of a reaction, you can actually look at that glass bulb under a magnifying glass. Do you see active scratches or dents or dings? One of the things I want to talk to you about is actually something one of my customers ran into. And it's a sort of a lesson learned. pH 7 is a buffer that you should never use as a single calibration or as a single verification point. Does anybody know why using a pH 7 buffer as a quick verification is a bad idea? Just put your thoughts in the chat window. Single point error, that's one reason. But if you're just doing a quick verification, a single point, as long as you did a 2-point calibration, you're fine. But verifying on pH 7 is a bad choice because pH 7 in an ideal world should have a reading of what voltage? If everything is perfect, what's the voltage? Put it in the chat window of a pH 7 measurement. 0, exactly. What measurement will you get on a broken pH probe? Also 0. So let me tell you a story. I had a customer who had a last minute panic and they dropped a whole tray of pH probes and they had a big process that they needed to run the next morning. Actually, they needed to go in about 1 for inoculation and they were panicking. So they called and they ordered a pH probe for next morning, 8 a.m. delivery. No problem. Our factories, and we have a facility in Reno, they're in the Bay, overnight, easy 8 a.m. The sensor arrived and their tech overslept and was running behind and was having a hard time getting everything done. So she grabbed the pH probe and she opened it up and she put it in to a pH 7 buffer and said, I'm going to trust the factory calibration and I'm just going to check and see if it's good. Great. She rinsed it. She put it in the autoclave. It went into the autoclave. It went into the bioprocess. And about an hour later, I got a screaming call from her manager because there was a stream of blue liquid floating in their bioreactor. The probe had broken. And he was not happy because it cost them a lot of money because they had to throw out that entire bioreactor. They had just inoculated and it let go just not long after. The problem is, when we started talking, I asked her to go into the box and send me a picture of the box because honestly, I assumed something had gone wrong on our end. She took a picture of the box and it was a little banged up. And then she took it open and she actually had a picture of the watering cap still sitting inside the box. She just left it in there. And instead of clear liquid, the liquid was blue. The probe had actually cracked in transit. Okay. So if she had visually inspected up front, if you see blue liquid in your watering cap, that's already an indication that there's a problem. Then she did a single verification and she got the bestest result ever. It was 0.00 millivolts. She was thrilled. She used a pH 7 buffer. If she had done a full calibration at 4 and 7, first of all, she wouldn't have been able to calibrate. It would have failed calibration, so she would have not used the sensor. But if by some miracle she would have calibrated and it somehow calibrated and she'd gone back to a verification, it would not have verified because there's no way the probe would have been responsive. So there are many steps she could have done in that case to avoid having to explain to her boss why they had to throw out an entire bioreactor. But the key thing was, if you use a pH 7 buffer as your validation, a broken probe also gives a 0 millivolt answer. And some pH bioreactors will consider 0 equals pH 7 equals awesome. So something to think about. So we talked about different kinds of sensors. We're going to talk briefly about intelligent pH sensors because this is the way, exactly, Doug, a broken clock is right twice a day. Intelligent sensors is the way a lot of the world is going. As we move into manufacturing, we're moving into the digital age instead of analog. The traditional bioreactors and everything were all analog bioreactors, analog signals. The problem with analog signals is they're weak signals. They're prone to a lot of problems. If you think about an analog sensor, which was the only sensor we had available to us for a long time, so they're still heavily used, but most of the new bioreactors coming out are not analog. 80% of the cost of ownership for a pH sensor is based on the service, the maintenance, the calibration, and the documentation you have to do. The smallest amount of it's based on the sensor. So if you take into account all the hours in the day, the chemicals, and everything you need to do to maintain and verify that your sensor is going to work and that you can trust the sensor in your next reaction, it's a lot of work. So is there a better way? If you think about the workflow for an analog pH sensor, this is what you need to do every single time. And this is assuming everything works. If you fail, you have to start over. So you get a sensor out of the closet, you gather your buffers, and you go over to the bioreactor. You attach the sensor to the bioreactor, you calibrate it at the bioreactor in your buffers. Oops, you failed the calibration. You got to go back and grab a new sensor. You attach it, you calibrate it, you insert the sensor into the bioreactor, you put it in the autoclave, and you sterilize. You document everything you just did. You troubleshoot your active process. You recertify the sensor. You check. You calibrate it offline, you put in your process, you take a grab sample, you go to the bench, it's a different value, you tweak it, you document that you had to change everything. This happens all the time. And if the sensor fails in your process, that's a problem. That could end up with you throwing out the entire process. In really critical processes, there's often what's called a redundancy in sensors. So they'll have enough headspace ports in their process so that they can have 2 pH sensors and 2 DO sensors just in case one dies during the process, because they don't want anything to go wrong. The worst thing in the world that can happen is a process deviation. If a sensor fails during a cell culture and you are regulated by the 21 CFR, by FDA, by anything, you have to write what's called a process deviation report. You might have to repeat the experiment. You might lose the batch and have to throw it out. You're going to have to do a root cause analysis. That can take a lot of time. If you validate that your stuff is still good, you have to write a very lengthy document on process deviations that you have to submit with the product. So you just don't want to have them happen because it's a headache and an entire department gets involved and people can lose their jobs over these things. The whole point of having a good process is to minimize your risk, and a failure is a maximized risk. So what's an ideal workflow? What would be simpler? I wish I could grab a sensor, put it in, sterilize it, certify it by doing a grab sample, making sure it's good, and I'm happy. That's ideal, right? I don't have to grab another one. I don't have to verify it. I don't have to write process deviations. If I grab a sensor out of the closet that's already calibrated, that's my ideal. And that's possible with something called an intelligent sensor. One example from Hamilton is what's called our ARC pH sensors. It causes a 45% reduction in cost of ownership because you have very little maintenance. Your documentation can be automatically handled in that software I showed you, and your calibration is done once in advance, and you don't have to recalibrate and recalibrate and recalibrate. It's kind of a cool toy. Okay, I get to play with toys. That's why I'm in sales. So what does a smart sensor look like? Well, instead of going, an analog sensors have to connect to transmitters. Transmitters then convert that analog signal into a more robust, stronger signal that your biocontroller can monitor. This does not require it. The sensor is here. It actually has a tiny little micro transmitter built into it, so it does not need a transmitter. You can have a Bluetooth adapter to it, so you can actually walk around your lab with your cell phone and check in on your probes while they're operating, and it's still sending signal. And there's a software for both your computer, your tablet, and your computer available. So it's a robust signal. It's a digital signal. It's very, very strong. You don't have signal integrity loss. You don't have the problem with analog sensors if there's vibration, if somebody flicks your cable, it can actually cause spikes in your signal that your bioreactor doesn't understand are not real. If an oven turns on nearby with an analog signal and there's a line current voltage that causes a 60 hertz current surge, you can actually see that sometimes in analog probes, which can lead to incorrect byproduct or automation or feedback loops. So having a digital signal that's not impacted by any of those is incredibly useful. The software has a lot of built-in troubleshooting and diagnostics, and you can scan the buffer and have all of that information enclosed in the software, so you don't have to look it up. The software already knows what your buffer tables are, and it includes them for all of the major manufacturers of all buffers. What's kind of cool about it, there's a sensor head on here that gives you a health card. Green is good. If it was yellow, that means there's a warning. That doesn't mean the sensor's not measuring. It just means maybe it's out of range. Maybe you set it to give me a warning if my pH should be between 7 and 7.4. You set it to give me a warning if I go outside that range. If it's red and solid, it means there's a there's a good sensor error. And if it's flashing and the sensor's connected, it's not sensing the sensor. And that's another thing that could be going on. And you don't want to have it not sensing, because that means you've either had a failure in your cable or you've had a failure in your sensor. But because it has that quality indicator that we showed you earlier, if your sensor health has 100% at the beginning of your process, that gives you a lot of comfort that at the end of your process, your sensor is going to be working through the whole thing. And if your quality indicator went from 100 at the beginning of a process down to 50 at the end or 60, that's going to tell you, something happened. Maybe I got a biofilm formation. Maybe I have a crack. Maybe something got damaged when I was handling. This is another way that you can actually test the sensor directly in the bioreactor, which you cannot do with analog, because you can have the sensor, the Bluetooth head on top of the sensor when it's in the bioreactor. So you calibrated it, it was good, you put it in the autoclave, it came out and something happened. You can actually put the sensor cap on and figure out what the problem is without removing it. Troubleshoot, figure out, is it a cable, is it a problem? Maybe you're getting a great signal out of the Bluetooth, but you're not getting any signal read into your bioreactor. It could just be that your cable died. And replacing a cable is a lot faster than replacing an entire sensor and throwing everything out. There are several versions of software. We don't need to go into it a lot, except that the cool thing about the advanced software is that it has 21 FDA 21 or CFR 21 Part 11 compliance. That means you can get full traceability, full audit trails, all of that. If you are going to manufacturing and you have a drug that's going to be, I don't know, a COVID treatment, vaccine, you want to have and must have legally a full traceable audit trail of everything going on in your entire process. And this will do that trail for you, which is kind of nice. So Arc Air and the Arc sensors, the intelligent sensor, actually reduce your operating costs. They give you a really cool sensor dashboard. You can actually log data in them. They give you diagnostics. And generally, they're just kind of a cool feature that takes a lot of the data tracking out of your work for you. So that's all that I have. My email is there. My phone number is there. I welcome you to reach out and call me if you have questions, if you need information. You're welcome to connect with me on LinkedIn as well. Just tell me where you met me and I'd be happy to chat. If you guys have any questions about pH, this is the time. Drop it in the chat window, put it in the question and answer window. I am here to answer your questions, assuming you're still awake. Okay, so Mark asked, This is great in aqueous media. How do we calibrate non-aqueous electrodes if buffers are aqueous? Well, the first thing is pH measurements require aqueous. You have to have at least 5% water to be able to even take a pH measurement. So therefore, you're going to need, it's an aqueous measurement. That's the short of it, Mark, is you have to have water in order to do a pH measurement. And I know that there's such things as organic acids, but unless there's water in there, they're not measurable with typical pH meters. So thankfully, Bioprocess, we're always in some sort of water environment. If you guys have questions and you don't want to ask them here, or they come up the minute you log off, feel free to drop me an email. I usually get back to you within a few hours to a day. And again, I'm more than happy to answer any questions. And you can reach out to Doug. I expect this will be loaded up to his YouTube channel in a couple of days. I'll get him the recording tomorrow. So other than that, Doug, is there anything more I can help you with?
Yeah, Lee, thank you so much for, again, this presentation. And as you were demoing in the background there, I love your setup, by the way. That's really awesome. It made me remember the in-person demonstrations you did for us in the past. And I know a lot of the people on this call are local. Some of them work at companies, some of them work at academic institutions. And I know right now we're under a situation where that's not possible, but I know you're probably raring to go once we're ready to go back to face-to-face and do that as well. But I love your demo station back there. I mean, it's always great to have hands-on as well when you're doing these things with the participants as well, so.
I am. And if, anybody out there is working at a company and your company is interested in some pH best practices, I also do this. I do this presentation probably once a week for some local company to help train their local reps. And it's very generic. I talk a little bit about the Hamilton probes, but 95% of what I talked about doesn't matter who made the probes. So I'm also more than happy to help you out there if that helps.
Great. Well, I don't see any more questions. I think that's it for today, huh?
Awesome. Well, then I'll give you 15 minutes back in your day because we're done a little early, and I appreciate you all giving me some time.
Thank you, Lee.